can never be locked down. I will be your moderator for today, Marik Neri from the Institute of Mathematics in UP Diliman. Our speaker for today received his undergraduate and graduate degrees in electrical engineering from the University of the Philippines, Diliman, as well as a graduate degree in computer science at the Kyoto University, Japan. He did his postdoctoral studies at Université Libre de Bruxelles, I hope I pronounced that correctly, Belgium, on swarm robotics, Bruxelles, Belgium. His current research interests revolve around applications of deep learning, probabilistic machine learning and decision making, swarm robotics, and computations to problems in environment, healthcare, and education. Currently, he is a professor at the Department of Computer Science of the University of the Philippines, Diliman, and he is the laboratory head of the Computer Vision and Machine Intelligence Group of the same department. Let us warmly welcome Dr. Prospero Naval, who will give us a talk entitled A Short Introduction to Deep Learning Architectures for Time Series Modeling. Dr. Naval, you have the, sasabihin ko sana floor, but now you have the screen.
Hello? Hello, can you hear me well?
Yes, sir.
Okay, great. So I'm Pros Naval from UP Diliman. This morning, I wish to talk to you about deep learning models for time series data. So many of you are familiar with deep learning methods, especially the CNN techniques to processing image data. CNNs have achieved state of the art performances in many computer vision tasks. We also know that there are many kinds of CNNs. You have the Linet, the AlexNet, GoogleNet, Inception, VGGNet, ResNet, YOLO, DenseNet, etc. So they are great for object recognition, for semantic segmentation, video analysis, and many others that require processing of image data. Image data from our cameras is just one among the many types of data available out there. There's also data coming out from various sensors, such as those from the Internet of Things. There's also text data from natural language processing that we need to process in order to understand user sentiment, for example. And there's stock market data that we would like to analyze. There's also DNA data from biological experiments that we would like to understand. So many of these are time series data. So in this webinar, I will introduce to you a class of deep learning models suited for processing time series data.
Sir Pros,
Yes. Okay.
sometimes your mic is going off.
I think there's something wrong with my connection. Can I switch to another connection? If you give me 30 seconds or so,
Yeah,
Yes.
automatic naman yan if
so we have a
you
better
sign up on the username and
connection. So, it says here unstable connection.
Yes, sir.
So sorry for this.
No problem, sir.
So we'll have to switch to my cell phone.
So yes, sir. I will just be posting announcements muna, sir. Okay, for the participants, if you have any
Okay. So
questions,
I yeah we're okay. Am I coming in loud and clear?
yes,
Hello.
sir. Yes,
Okay,
sir.
great. So we can continue just now in another connection. So as I have said, in this webinar, I will introduce to you a class of deep learning models suited for processing time series data. So we will cover the following topics. I will talk about the basic deep learning time series models, the RNN, the recurrent neural network, which is the most basic one, and then the bidirectional version of the RNN. And then we have the LSTM, or the long short-term memory network, which is an improvement over the RNN. Then the gated recurrent unit, or GRU. And then we will proceed to discuss the sample applications of RNN and these different variants that we have seen. And then we will move on to a brief discussion about word embeddings, which is so important for natural language processing. And then I will explain attention mechanism, which tries to address the basic shortcomings of the models that we have that we'll be discussing. And then we'll finally wrap up our seminar by talking about the transformer, which is the state of the art uh, time series model, which is the building block of two important models called BERT, okay, and GPT-2. So these are the latest models for NLP. Um, Although, of course, I will not talk about these two because they deserve more time than than what we have available this morning. So just to level out the expectations, we will not cover the training of these models. So no discussion about training because this requires more time, and this contains a lot of gory mathematical details, which is better discussed some other time. So after all, this is just an introductory talk. Now let us start by considering two examples of time series data. The first one is that of stock market prediction. Suppose we have some money in the bank and your friend is trying to convince you to invest in a particular company. So, given this information that we have on screen here, it says here that the current value of that company is 2,148.36 at this particular time, 1:30, 1:25 in the afternoon. So, obviously, would like to know how this thing will proceed. So, what will happen to this value after 5 minutes? No? Given this information, only and only this information, it would be irrational to say yes. But what if we are given more information? Say the price of the share for the past few hours. So here, okay, so we probably will not be very convinced because there seems to be no interesting pattern. But what we observe here is that there's a lot of noise and that the signal to buy or to sell or to hold is buried in this noise. And we might ask, what were the values over the past 5 days? Okay, so there seems to be a little bit of pattern here, but still not very convincing. How about the past 5 years? Okay, now we're beginning to see a pattern. So we can then probably compute the differences between the share price now and what it was about a year ago around this time, and so on and so forth. So and then you make a decision. Um, then let's take a look at another data set. Everyone's favorite data set these days. No? So I'm sure all of you have seen this data many times. Even in Facebook, you see this data all the time. So this is the COVID-19 epidemic curve for the Philippines. So you probably would like to predict the number of new cases for the following day. And obviously, this data is very important. And this data is also very noisy. Um, but it is harder to make a prediction given this information. So how are these two examples different? Of course, they're totally different in many ways, but I'd like to point out that the stock market data is big data with hundreds of thousands of data points, while this COVID epidemiology data is just less than 100 points, 2 months worth of information. So here we have big data versus small sample size data. And now the important question, okay, should I use deep learning? Should I use the methods that I will be talking about today or not? Well, it depends. So deep learning is not the answer to everything. So examples of machine learning, it says here machine learning, but let's this machine learning here basically is traditional machine learning because deep learning is also machine learning. So examples of traditional machine learning are logistic regression, decision trees, shallow neural networks, k-nearest neighbors, naive Bayes, Bayesian networks, support vector machines, random forests, etc. So there are literally hundreds of them if you include their variants. While deep learning is great, we know that it will not perform well when training data is not abundant. In fact, traditional machine learning beats deep learning in many applications where data is expensive to produce. So, in many experiments, just to get a data point costs a lot of money, especially for the biologists. So, to just get one data point, you need to do a lot of experiments, spend a lot of money, and so on and so forth, just to get that single data point. So, obviously, we'll not have a lot of data. So, how big is big? Depends on the problem. If you have a few hundred data points, traditional machine learning will work much better than deep learning methods. But when you're talking about 100,000 data points, then deep learning is the way to go. So let's take a look at the more familiar CNN. So this is the diagram of the first CNN. The first CNN is not the AlexNet. No? The first CNN is the Linet 5, invented by LeCun in 1998. So if you look at the diagram here, there are thousands of parameters that you need to train. And that's why you need lots of training data. Now, let's talk about time series data. So examples of this are stock market data, data from epidemiology, speech, ECG, text, DNA sequence, and so on. So for time series data, the values on successive time steps are closely related to each other. So that's one characteristic of time series data, that they have to follow a sequence, that the values cannot be interchanged. Okay, the values cannot be interchanged. So if you switch two values, then you're changing the data altogether. If you shuffle the data points, you're definitely destroying the data. So the sequence is important. Now, although for text and DNA sequence, these data do not necessarily have a time component, we can loosely consider them as time series since they are, after all, sequential in nature. So this is what differentiates time series data from data used in classification problems. A typical classification problem assumes that the data is IID, independent and identically distributed. Sequential data, on the other hand, is not IID for obvious reasons. So crucial information is lost if the values are treated independently. This is not like what we see in classification problems again. For example, the naive Bayes. The naive Bayes, as we know, has this independent assumptions among the different features. The spam filter is a typical application of the naive Bayes algorithm. But we know that it works. No? The naive Bayes algorithm works even when this violation when this assumption is violated. So your spam filter will work equally well even if the words in your email are shuffled. And that's the bag of words model. No? So you just put together all the words in your document in a one vector, and that's it. Now, obviously, this is not true for time series data. Again, crucial information is lost if values are treated independently. Let's take a look at the example here. The cat chased the mouse. So that's a sentence. It means something. Now, if you just interchange the two nouns here, the mouse chased the cat, it obviously means something else. So here, the bag of word model fails. So some of you might be thinking, so how can I represent words in a neural network? So assumption is that you know something about neural networks, and neural networks process obviously numbers. The way to process words in for as inputs for neural network is to use the so-called one-hot encoding. So what we do is we define a dictionary of say 10,000 words. We sort them alphabetically. These words are sorted alphabetically. The first word in that dictionary is encoded as a vector with all the elements zero except the first element. And the second word is encoded, in this case, aardvark, is encoded as a vector with all elements zero except the second element, and so on. So that's how you encode your word. So instead of putting zoology, for example, you just put that this particular vector as input into your neural network. Now, suppose you want to construct a sentiment analyzer. You want to classify the sentiment of a particular sentence. And to make things simple, let's just say that we'd like to just classify whether that sentence is happy sentence or a sad sentence for simplicity. Obviously, we can just increase the number of layers here to accommodate more complex sentiments. Can we use the more familiar convolutional neural network? Now let's attempt to do that. Here we have a sentence that's being presented to the neural network, to the CNN, as a sequence of words that are one hot encoded, and the output should produce a +1 for very happy and -1 for very sad, and probably neutral, zero. You get zero for neutral. But this will encounter problems. First, sentences are of variable length. So how do we accommodate a variable length sentences? And for the second example here, yeah, you have a four-word sentence. So there's a missing input to the fifth uh, input node. Say it also does not directly encode the word ordering within the architecture. For example, suppose our okay, so here we have a four-word sentence. Analytics must be fun. But what if you would like to process the sentence? Data analytics must be fun. So this analytics here, so the first X1 here will be data, and X2 here will be analytics, and so on. So we move everything down. So as you can see now, the neural network will probably get confused a little. So in other words, the neural network does not encode the word ordering within the architecture. So there are deep learning models that are more suitable for processing sequential data. So we have the RNN, or the recurrent neural network, which is the most basic deep learning model that can process sequential data. We have the LSTM and the GRU, the gate recurrent unit, which is a simplified version of the LSTM that works just as well as the LSTM. So now let's take a look at the RNN. Okay, so this is the RNN. So it looks scary, right? So so these diagrams look scary, um, especially the right one, the second one here. So, but let's just ignore this second diagram, the second figure here, figure B, and focus on the first one. So here, what we have is an input layer that accepts an input for time t, xt, which in this case is a one hot encoded word. It could be anything. It could be another type of data. For example, it could be the stock market prices of all the companies in the standard and poor 500 at a particular time t, whatever you like. Okay, but for now, let's focus on focus on words because these are easier to understand. So NLP is easier to understand than just putting in numbers. Um, and then there's also that hidden layer with a value ht, which represents some quantity which we will talk about later on. Then there is this self loop that changes the hidden state of the network after the input of each word in the sentence. So there's the okay the self loop here. Then there's the output layer that produces a value associated with the input xt for time t. Then you have three matrices in the diagram. We'll talk about it again later on. So now it's simpler than actually what we originally thought. So it's no longer that scary. So it's just anyway a set of layers. So we are very familiar with this in neural networks. So you have the input layer here, and then you have your hidden layer, and then you have your output layer. So very simple. It's simpler, much simpler than your CNN, which has all sorts of things like convolution layer, and all sorts of stuff. So this is much simpler. Now, suppose you would like to use this RNN to predict the next word. Okay, predict the next word. So each time step has an input. Um, okay, so an input layer, a hidden layer, and an output layer as well, like here. And note that the weights are fixed for all time steps. It's important to remember this, that the weights are not changing with time. Okay, we have not talked about training, but once we have trained the neural network, this RNN, the values of the weights W's, the W's here are fixed. Again, let's go back to the language modeling task where you would like to predict next word given the previous words. The RNN has been trained to predict the next word. Suppose that we have trained the RNN to predict the next word given the previous words similar to what we have here. Okay, and well, this is something familiar, isn't it? So your smartphone predicts the next word for you when you're typing your text message, which is sometimes very annoying, especially if you're composing a message in Filipino and then it suggests an English word. So this is the so-called autocorrect. Sometimes they call it auto wrong. Okay, so autocorrect. So this is how, I don't know how it works really, but this is similar, not to what we have in our smartphone. First, we initialize our hidden vector. Then for your first input, you send the first hot encoded vector for the word the, and this vector is multiplied by this matrix here. Then there's some computations that are done to produce H1, and this H1 is multiplied by HY, and so on. So we'll see the computations in the next slide. But as you can see, there is this unrolling, unfolding. Okay, so the vector, sorry, the network unfolds itself over time. So this second figure here is the unfolding and the unfolded version, the time unfolded version of the first of this first figure. Now let's take a closer look at the computations. So here you have your input xt. Here is your xt. You multiply that by this matrix, the input to hidden matrix, and then you add that with the product of the hidden to hidden matrix and the previous value of the hidden state. Okay, the value of the hidden state in the previous time step. And that's now, you take the tan h of that, and that's now the value of your hidden state at time t. So these are all vectors, by the way. And the output is just the product of the hidden to output matrix here and this HD here. Then you have probably softmax on top of your YH to generate the probability. So it's really very simple. So you can probably, some of you can probably just write some code to generate this to make it, make a recurrent on RNN right now if you wish. Now let's continue to analyze the language modeling example further. So as we said, we are going to form a dictionary, and in this case, let's just say that we just have four words: the, cat, chased, and mouse. So the one hot encoding for the is 1000, for cat 0100, and so on. Now, this network has been properly trained to recognize the next word, and the output has to be converted to probabilities using softmax. So here we have not converted the output to softmax. That's why these are just right now the log probabilities. So when testing the RNN, we often put a start token as the input for x0, and the end token terminates a sentence like the period. And since the start token is used during training, the model will select a word that often starts text segments for, in this case, the, because many sentences start with the. And okay, so we have here your log probabilities. We convert this into probabilities using softmax. We are not going to use the argmax of the outputs. What we're going to do is we sample, okay, from this distribution. Okay, we sample from this distribution. That is the way to use this RNN. So that way your resulting sentence is not going to be the same all the time because there's sampling. So this idea has been tested many times, and they, instead of using words, some authors uh, use the characters and train the RNN on the Shakespeare, the plays of Shakespeare, and this is how the output look like. So after 5 iterations, it still doesn't have many. a lot of sense, but after 50 iterations, you now have something very interesting coming out. So uh, these are okay, error free after actually the end of trainings. And if you observe, even the indents in the format of the text would be similar to the place. Now, there are several types of RNN. Well, you have the more familiar one that we have discussed, that we have seen. Okay, we've seen this before. So this is the sequence to sequence. So both inputs and outputs are sequences, like for example, yeah, your your language, your next word a predictor, and you have also your stock market predictor. The output would be the next predicted output for the next time step. So it's a sequence, and the output is also a time sequence. And then you have another type, which is the vector to sequence. Okay, so here your input is just one vector, and for the other time steps, there's no there are no inputs anymore. Okay, but the output would be a sequence of words, for example. So this is useful for things like image captioning, where our input is an image, is a picture, and the output would be a description of the picture itself. Then you have a sequence to vector um, um, application. So here it's similar to the sentiment analysis example that we have has that. So you have a sentence, and we are interested in the sentiment for that particular sentence. So that's an example of a sequence to vector. And finally, we have another sequence to sequence, similar to this other one, but this time the outputs are sort of delayed. Okay, so you have missing outputs here. Then here you have missing inputs. So this is the case for machine translation, where we want to first end the sentence before we translate that particular sentence. So we cannot translate word for word, obviously. So if you do that, the translation will certainly be very bad. And we'll see that later. So we'll talk about machine translation later. Some applications benefit from knowledge of both past and future states. So, it's looking at the past words, but even the future, future words. So if you're given an entire document, you can do that. And in this case, there are models that exploit this type of data, and that's the bidirectional RNN. I think I have to go a little bit faster because we're just in slide 20. Okay. So these are the equations for the bidirectional RNN. It's quite similar to the one that we have. So basically, you have just two types of RNN, one going in the forward direction and the other one going in the backward direction. And these are the equations governing the hidden states of the forward and the backward parts of the model. The output would be the combined outputs, yeah, combined outputs of the stack of hidden layers. So again, you can have multiple layers of RNN for more complex models. So similar to the shallow network that we are very familiar with. So you can have here three hidden layers. So this is for applications that are quite complicated or complex. So it's typical to have two, three layers in practical applications. Now let's go to the long short term memory network. We have a problem with the RNN, and that is the RNN can only remember relatively short sentences. And this is due to the way it is trained. So, as you probably know, when you train neural networks, you have to do backpropagation. And for the RNN, this backpropagation method gives us headaches because the 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 products, okay, you have multiplicative updates of the weights, and these products actually either go down to zero, they diminish, they vanish, or they explode. So this is the so-called vanishing and exploding problems, for training neural networks. So the RNN is a bit susceptible to this kind of problem. So the vanishing gradient problem or the exploding gradient problem. Now, to solve this, researchers have developed the so-called long short-term memory network, or LSTM. So the LSTM has four gates: the input gate, forget gate, output gate, and the new start gate. These are all p-dimensional vectors. So you have input gate is just a vector with p elements, and this for simplicity, think of these elements as assuming values of zeros and ones, but in reality, they actually continuous values. But just for the sake of analysis, just think of them as just consisting of values of zeros and ones. So just like in the RNN, the HT represents the hidden state, and there's also the hidden vector CT, which is the cell state. So the CT here, the new cell gate is denoted as C or CT. So the cell gate may be seen as some kind of long-term memory that remembers part of the information in the earlier states by a combination of partial forgetting. Okay, so this is the CT minus one here is your value from the previous time step, and you sort of multiply that by f, which tries to forget or remember that value, and then you include, of course, you add that to your input. um so then uh, just to make things easier to understand here, the cell state might remember an opening quotation character by changing the signs of one of the elements in the p-dimensional vector, and this p-dimensional this element in the p-dimensional vector will go back to its original sign when a close quotation in the input is detected, for example. So that's how these things work. Now, okay, so these are just a few details of how this thing operates. We'll not go into this anymore because we're running short of time. Okay, so yeah, important thing to remember is that the long-term cell states act like gradient super highways that leak into the hidden state. So that's how the LSTM remembers the data from the previous states. So even if the state is that of say n minus 20, for example, or 50. So that's remembered by your LSTM. Now we have well, obviously, if you look at the equations, this is a bit well, this is complicated. So the GRU, or the gated recurrent unit, is a simplification of the LSTM. So it does not use explicitly cell states. It uses a single reset state to control information in the hidden state. We have the um, we have here, okay, for the GRU we use two matrices W and V, and the Z and R are the reset and update gates. These values, their values, the values of Z and R are computed according to these equations, and these are used to decide this equation rather, and these values are used to decide how much to change the hidden vector here, um, and okay, you multiply that with v and okay, you get your ht. So this dot c dot here is the element wise product. um, so the LSTM is similar to the GRU. The GRU is the simpler version. They exhibit similar performance. Which one is better depends on the task. GRU is simpler, efficient, easier to implement. It performs slightly better with less data, but when you have lots of data, LSTM is preferred. And there's a lot more experience with LSTM than GRU. Okay, so now the more interesting part, perhaps. So, how do you apply all this? How do you apply the RNN, the LSTM, and the variants? So they are well, they're applied for. So think of this as just okay, applications of all these types. No? So you can apply these three to automatic image captioning. For example, you present the neural network with this picture here. The neural network, well, the entire system will produce a description of the picture, cosmic winter wonderland, something like that. Okay, so let's analyze a bit how this works. So we are familiar with the CNN. So you have your image is submitted to the CNN, and it produces a vector output. That vector output is now the input to your LSTM or your RNN or your GRU, if you like. So it provides this vector v here is the image representation, and use this update equation to train your LSTM. By the way, the CNN and the RNN, or the sequence model that you have, are trained or have to be trained jointly. Of course, you can initialize the CNN with the weights. You can train them separately, but the outputs of the output weights, or the trained weights, will just serve as initialization for the joint training of the CNN and the sequence model. So interesting application. The other one is that of machine translation. Um, so here, you want to translate the sentence. I don't understand Spanish. So the outputs are not yet there. So you have here this RNN1, and this part here would be your RNN2. The output, no entiendo español, would only be made available once you have finished the sentence. So obviously, you cannot process that sentence unless you encounter the end of sentence or the period. So this is the end of sentence. When the network encounters the EOS, or end of sentence or period, then that triggers now the production of your translation. Okay. So here we have two RNNs or LSTMs with different weights. The first network has no output. This is your first network, but it tries to accumulate information about the source sentence and the hidden states. Then you have your end of sentence symbol, the period perhaps, that triggers second network to output the words for the target language. So that's your machine translation example. So this tends to work poorly for long sentences. And one solution that's been proposed is to to provide an input language in opposite order. So which means that the first entry here would be Spanish. Okay, Spanish understand don't I. That kind of sequencing for the input uh, would produce a better translation apparently than compared to just the natural word order. I don't understand Spanish. Then the RNN, LSTM, these are also used for question answering systems. You can ask the network, what is the capital of China? End of question. And the second part will answer the capital is Beijing. End of answer. So this is similar to the machine translation example that we have seen here, except that we have trained it using questions and answers. So QA has a greater level of reasoning because it has to understand relationships between people, places, organization, and so on. And this related to information extraction. Then you have sentence level classification. So I love this iPod, and okay, you have a positive sentiment and so on. So this is for for sentiment analysis. Then you can also use this network for token level classification, where you'd like to determine the token type. William is a person, Jefferson is a person, Clinton is a person, and then in this New York, these are locations, and so on. So and these other words are classified as others. So these linguistic these outputs here are going to be important for NLP. This is called the named entity recognition problem. The outputs are tags rather than next words. Let's now talk about word embedding. Um, so, what are word embeddings? So, word embedding is a learned representation for text where the words that have the same meaning will have the same representation. So, for example, sweat and perspiration. So, these are the same, okay, right? The same concept, but different words. So these two words should map to the same um, input, uh, representation. So in the one hot representation, obviously these two will have two different representations. So this idea of word embedding is perhaps one of the most important breakthroughs of deep learning in natural language processing. So it's basically a mapping from words to vectors. You have a mathematical embedding from very high dimensions, for example 10,000 dimensions here. Okay, you have a 10,000 word dictionary that you're trying to process, but you're going to reduce the 10,000 dimensional one hot encoding into a perhaps 300 dimensional continuous space word representation. So this is much lower in dimensionality, and obviously there are lots of advantages to using this. It's going to make your computations much faster. 10,000 dimensions versus 300 dimensions. It's a lot of savings. Here the input is sparse. Everything is zero except one. While in the case of the word embedding, the output is dense. Um, Word embeddings have very interesting properties. So suppose you have here the word embedding for king is residing is a point in some 300 dimensional space, and queen also a point in some 300 dimensional space. The distance between these two is more or less the same as the distance between the word embedding vector for man and woman, and the direction is also the same, more or less. So very interesting. So it sort of tells you that, okay, if I know the relationship between these two, king and queen, and I am presented with an input man, using this relationship, I can figure out that vector woman. So yeah, male to female relationships, verb tense, walking to walk, swimming to swim, country to capital. So Ankara, Turkey, Ottawa, Canada, and so on and so forth. So very interesting representation. It's not just some arbitrary, ordering in some low dimensional space. No, there's that ordering is has very interesting properties. Yeah, you generate this word embeddings using word2vec. We will not talk about this in the interest of time. Let's now talk about attention mechanisms. So, um, humans, when we are presented with sensory information, we focus on a specific portion of the data that we have, depending on the task that we have at hand. For example, you're probably looking at your computer and you're looking at a word, not the entire picture, the entire computer, not the entire slide, but you're probably looking at a particular word, or probably you're looking at the point where my pointer is, okay. So okay, so you're basically paying attention to that word, to that point, or to that interesting color or whatever. So that's the idea, that's the inspiration for the attention mechanism. So in natural language processing, there are words that are more important than others. Uh, Words that are less important are the articles, okay, in some sentences they're not even included. No, so Japanese, Chinese, I don't think they have articles. But these articles are important for the other languages, for the Western languages. So, but the nouns obviously are very important. The names of persons are very important. And for machine translation, the alignment of words in the source and target language is important. And I'll illustrate this shortly. So if you don't understand this, you will or should in a short while. Okay, so let's go back to the machine translation application of the RNN. Okay, so here we have the example that I've shown before. I don't understand Spanish, no entiendo español. So here we can consider the first RNN as an encoder and the second one as a decoder. The encoder transforms the source language, the source sentence, I don't understand Spanish, into a fixed length representation. So the entire sentence is actually just you know encoded in here, the output here, and that output is the one that's multiplied by this WS here, and this is the so-called context vector, by the way. So this context vector is the basis of the translation. So there's a problem here. Why? Because you cannot, basically we are trying to cram the meaning of the entire sentence into a single vector, right? So you might have a very, very long sentence. German sentences can be notoriously long. So there's even a joke that when you are learning German, German is speaking. you're waiting for, you're gasping for breath, no, to wait for the end of the sentence, because that sentence is very long. It could be one paragraph. There are authors, there are German authors that they like to write using very long sentences. One sentence might be equivalent to one paragraph in English, for example. Well, actually, I don't know German. It's just it's told to me that. Okay, so now how do you capture that very long paragraph like sentence into a vector? So it's very hard, right? That's why this machine translation application for RNN is very challenging. So okay, so the decoder transforms the representation into the target sentence. To deal with the word alignment problem in machine translation, okay, okay, so obviously you cannot translate, for example, here, no entiendo español. No? So while in this case, there's a like the ordering is the same. No? So don't more or less know and then understand, entiendo, Spanish, Espanol. So the ordering is the same, but in many languages, for example, Filipino, Japanese, instead of the usual uh, verb, sorry, subject, verb, object, which is in the one the ordering for English, for example, a typical Filipino or Japanese sentence would have the verb at the end. So there's a shuffling of the ordering. So how do you take that into account? So use attention mechanism. And the way to deal with that is to use a matrix like this that tries to map, associate a particular word with another word in the target translation. So the first word, the, for example, might correspond, maybe not that, but this particular report here might be towards the end of a particular translation. So if it is the second word in the source language, it could be the fifth word, and so on. So that's so if you try to solve this using attention mechanism. So you pay attention to certain words, and these certain words are mapped to certain other words using this kind of matrix. Um, okay, so here, uh, so the attention mechanism allows the decoder to look back at the encoder's hidden state based on its current state. And the decoder is then able to extract only the relevant inputs. So here, yeah, you have hidden state HT1 here, okay, and HT2 is the hidden state of the TF word in the target language. So for attention-based methods, the hidden states here are transformed to enhanced states, which are the output of the attention layer. So this is your attention layer. So the goal of the attention layer is to find the source representation close to the target, to the current target state, HT2 here. Okay. Um, you have your context vector, and then you have your, well, we're familiar with the context vector. The context vector is just the output of the last word here. Okay. And then you combine that with the attention matrix, and you form uh, this H, capital H vectors here. Now let's go to the transformer. It's already 10 o'clock, and I think I have to. Yeah. Anyway, this is the last topic. So the RNN, LSTM, GRU, they rely on hidden states for sequence modeling in order to maintain historical information. And this historical information would be summarized in these states. Now, in the transformer, uh, there's this okay, the paper describing the transformer is the one by Vaswani. This came out in NIPS 2017. Attention is all you need. Okay, so okay, so they put a lot of attention to attention. Okay, so this uses the transformer uses self attention to compute the input and output representations. The advantage of this is, well, actually, there's many advantages, but one key advantage is that it's easier to parallelize the computation, especially during training, where you need to do a lot of iteration. Here, we would like to learn a context vector, which will give out the global level information on all the inputs and tell us about the most important one. And we said earlier that the attention mechanism allows the decoder to look back at the encoder's hidden state based on the current state. Um, in the transformer architecture, this idea is extended. We are not just going to do that, we're going to learn the dependencies between inputs as well as between outputs, and this is how it's done. To simplify, you look at this architecture is very complicated. To simplify, we just look at these two, this architecture as composed of an encoder here, encoder layer, and a decoder layer. And both of them, if you observe, are composed of a stack of identical layers with the following components. You have a multi-head self-attention mechanism and a position encoding and position wise feed-forward neural network here. So I won't go much into the details here because we don't have time anymore. If you wish, you can go to the original paper. So the important points are summarized in the remaining few slides here. Um, yeah. So here in this slide, it talks about the uh, scaled dot product attention. So the idea here is that the output is a weighted sum of the values where here where the weight assigned to each value is determined by the dot product of the query with all the keys. So okay here um, and then you have the multi-head attention. This makes it easier to train this network and also to during runtime to process the data because these things can run in parallel. Again, I'm not doing justice to this very important uh, uh, network, but since we're running out of time, I guess we'll have to wrap up. Okay, so they evaluated the transformer, and the results are amazing. So using the blue bilingual evaluation on this study, it's an algorithm for evaluating translated texts, which means that the higher the value, the closer machine translation is to a professional machine translation. Obviously, if you have machine translators, when they translate a text, even if they're all professionals, the translations are not the same. So it's very difficult to get a score that is close to one. So yeah, well, for the transformer, it performed quite well. Okay, so yeah, so this is your source language, and translation is shown here. Okay, so with that, okay, so you have the values here in percentage compared to the the other systems, the transformer um, got very good results. So references. So if you're interested further in time series data analysis, uh, especially the transformer, I'd like you to read this. Please read this important paper, and also this blog in Medium. Okay, I guess that's all. So I hope I have introduced you to these important models, and we did not talk about training, but I think with enough motivation, you can understand a little bit more uh, by going through the slides in the future. So, thank you for your attention.
Thank you very much, Dr. Prospero Naval, for that very challenging talk. And for me, a math person, the algorithms, the networks can really be inspiring. So it's the architecture of designing workflows in machine learning. We have some questions. A reminder to our participants, if you have questions, you have until 10:12 to post the questions. But I think we already have a